All right, so we're finally here. We're finally at Unit 3, where we actually get to apply the derivatives a little bit more. This first video is going to cover related rates, and that's actually a pretty big topic to have in just one video. But what you'll notice as you do more of these problems over and over is that there's kind of about 6, 7 major types of questions, and they just ask them kind of over and over with new variables and new missing parts. So, as you practice this, just keep an eye on what you're starting to see pattern wise, and that will help you solve these. Okay, so in general, related rates ask us to solve a problem, and a lot of times you have rates happening, like a rate of something flowing into another object, like I'm putting water into a tank, or maybe I have a rate of a speed of a car moving, and I want to see how that's affecting other distances. So there's a couple of steps that I have listed here on this first page about steps that you can take to solve these. And as we do the examples, I'll kind of relate back to these. But number one, you want to draw a picture and start labeling that diagram. Two, you want to figure out what the relationship is. And by relationship, I mean an equation. So, is it a right triangle and you're talking about the sides? So, Pythagorean theorem. Or is it a right triangle and you're using an angle? So, you can use SOHCAHTOA, sine, cos, or tan. Sometimes it's a shape like a circle. Sometimes it's a 3D object like a sphere or a cone. And once you get the setup and you have that relationship, you can then often do the derivative of that relationship and substitute in things you know and solve. So let's actually get into the business of looking at some of these problems. So in the first one, before I started involving actual real world situations, I involved you finding the relationship for just an equation. Okay, so in this first guy, we have two variables in our function x and y, but I'm going to look at them both with respect to time or t. Typically, that's because, for example, you could have an object being thrown into the air, and I can want to know how much that object's traveling horizontally, which would be maybe like an x direction, per time, and also a y direction, a vertical change per time. So more often than not, we actually want to define our variables in terms of time. So we are going to start with our equation, and then we'll pick up these givens in a moment. So let me start with what you're given. You're given this relationship on x and y, and we want to find them their rates, but with related to t. So what does that mean? Well, that means I'm going to do the derivative, but with respect to t instead of x. So, okay, let's take the derivative of x cubed. The derivative of x cubed is 3x squared. But because I'm doing the derivative with respect to t, I also have to include the rate of change with respect to x. So dx dt, I have to attach a dx dt. Kind of like when I was doing y derivatives with respect to x. Second term, negative 4y, but again, I have to attach my dy dt. Plus, the derivative of 5x is 5, but again, 5 times the rate of change of x with respect to t. Now, the nice one is 16, which is 0. So normally in the last unit, we might solve for one of these dy dt's or dx dt's. But in this case, it was easier to actually plug in what you know now. So for example, I know that I want to do this when x equals 2. So I'm going to plug in a 2 for my x. I know dx dt, my rate of change of x is 4. Minus 4 times my y value, negative 1 times, I don't know my rate of change of y, that's actually what I'm looking for, so that'll stay the variable, plus 5, my rate of change for x once again is 4. Okay, so this part right here ends up becoming 48, this is a 20, altogether that's a 68, plus 4 dt, equals 0. I'm going to solve for the rate of change of y with respect to t by subtracting the 68 and then dividing by the 4. And that actually reduces down to negative 17. So the y variable is losing 17 units for every unit of time. Okay, so now let's get into something a little bit more fun. Let's get into some real world scenarios here. In this first example, I have a ladder leaning against a wall, and this is a very typical AP Calculus problem. And if you don't want to do a 3D drawing, you could also just draw a triangle where this is the ladder and this is the floor and the wall. They do tell me it's a vertical building, which means that's a right angle. And they do tell me that the ladder is 20 feet tall. So I'm going to fill those things in. They also tell me that the base of the ladder is being pulled away from the wall, or you could think of it as slipping away from the wall at 2 feet per second. That means that this length is increasing at a rate of 2 feet per second. If it were getting shorter, if I was moving towards the wall, then I would make that a negative. So when you're getting bigger, you are a positive, and when you're getting smaller, your rate is a negative. Okay, so let's see what else we know, or let's see what they want. They want to know how fast is the top of the ladder moving down the wall when its base is 12 feet. Well, let's add that information in. I'm looking for how fast this is going down, because it will slide down when the distance from the wall is 12. Okay, well, first of all, the relationship here, this is a right triangle. I'm dealing with sides, so I'm going to use my Pythagorean relationship, which is x squared plus y squared equals z squared. Okay. None of these involve rates yet. And remember, I want to find how fast the top of the ladder is moving down, which means I want to know the rate at which this is changing. So I could actually just call that dy dt, right? Because that's the rate at which the y is changing. So I'm looking for that. But to introduce rates into equations, you would need to take the derivative so that rates show up. So, okay, before I get started, anytime one of your variables is constant, meaning it's not going to change, there is no change in its length, then if there is a constant, you can fill it in. So in this case, 20, the ladder length is constant. So I'm going to rewrite this with the 20 in there. You'll see why in a second. All right, so now let's take the derivative. This is 2x dx dt plus 2y dy dt. And then the derivative of something that doesn't change is 0. There is no rate of change, or well, excuse me, the rate of change is 0. So even if you had left this as z, when you did the derivative, you would have 2z dz dt, and the dz dt would be 0 because it doesn't change at all. So you can still solve it. I'm going to divide everybody by a 2 to make it a little nicer. So I'm going to get x dx dt plus y dy dt. All right, then I'm going to plug in what I know. Well, let's see. I know that x, the x side that I've labeled, is 12. I know that the rate of change is getting bigger at a rate of 2. I know, oh, I don't know my y value. How am I going to get that? Well, I know 2 of the sides of my right triangle, so I can just work backwards using Pythagorean theorem. And I end up with 256, which is just 16. So now I can fill in the y value. And my rate of change, well, that's what I'm trying to solve for. So I'm not surprised that that stays a variable. So then I'm going to subtract 24 and I'm going to divide by 16. And what we end up with is that your rate of change is negative 3/2. And I would leave it a fraction because that's nicer to work with. Are you surprised that that's a negative number? I hope not, because this is getting smaller. So you would expect the rate of change to be decreasing or having a negative value. Okay, so now we're going to take this and look at it slightly different. In question B, I asked you to consider the area, the triangle formed by the wall, the ladder, and the ground, so same scenario, but I want the rate at which the area is changing. That means I need to introduce area. So what is area of a triangle? 1/2 base times height. In a right triangle, the base and height are the legs, so more specifically, 1/2 x times y. Now, before I do the derivative, I'm going to check and see if x or y stay constant, but they don't. So unfortunately, I'm going to have to do the derivative. Yep, I'm going to have to use the product rule. So I get 1/2 derivative of the first times the second, but careful, you need a dx dt because you did the derivative of x, plus 1/2 x dy dt. Once again, I'm going to plug in what I know. What I'm looking for is the rate of change of area. So we're good there. And then I've got 1/2. My y value is still 16. My rate of change of x is still positive 2. My x value is 12, and my rate of change is still negative 3/2 for the dy dx. I found that in the previous question. And I believe that this all comes out to 7. And because it's area, it's feet squared per second. So I'm growing in area. All right, and then the last one that refers to this asks you to find the rate at which the angle between the ladder and the ground is changing. Whoa, if I want to find the rate of an angle, that means I'm looking for maybe like a d theta dt. So let's look at the problem again, but let's put in a theta where I'm looking for it. So I still have the 20, I still have the 16, I still have the 12. This is still a rate of 2. This is still a rate of negative 3/2. So I need a relationship on theta. So, well, theta is in a right triangle, so I have three big choices. I have tangent, I have sine, and I have cosine that I can use. Now, one of these sides is constant, so it's not going to change, which makes the derivative always easier to do, 20. So I'm going to pick a trig function that involves this hypotenuse. So let's do sine, for example. So the sine of theta equals the opposite side, which is y, over the hypotenuse. Now, oops, that's a z. Now, remember, I said if anybody is a constant, that you should go ahead and put that number in. So instead of a z, I'm going to have a 20 because that's going to stay constant. And also, I'm going to write this as 1/20th y because the derivative, I think, might be easier to see. All right, so let's do the derivative. I get cos theta, don't forget, d theta dt equals 1/20th. Look, that's just a coefficient, dy dt. Plug in what you know. This part's easy. The rate of change of y, just as before, was -3/2. This is where some people get lost. Cos theta is a ratio, guys. So go back to your triangle. What's the cos of this triangle, of this angle theta? 12/20. Oops, 18. Okay, then I'm going to multiply both sides by 20/12 and reduce. And I think that when I reduce here, I get -1/8. And I don't have a unit, so I'm just going to say unit per second. Okay. All right, this next problem is a cone, and it's a cone being filled, and this is a very common problem. I'm going to show you how to do it. It has a slightly extra piece to it, but the general idea is the same. So we have a tank, and it's a cone, and it's inverted. We know that the altitude of the cone, the tank, whoa, is 16. So the height is 16 feet, and the radius is 8 feet. Now be careful because sometimes instead of the radius, they'll give you the diameter, so you just want to make sure you're being careful. They say that the water is flowing into the tank at a rate of 2 feet cubed per minute. Well, first of all, 2 is a rate. And when I'm putting water into something or adding mass to something, that is a volume ratio. Or the tip off here is that your rate is cubic. So this is a rate of change of a volume. So, yep, dV dt. Okay, what do we know, or what do we want to know? How fast is the water level rising? Well, that's a rate of change, and water level rising would be a change in the height. So I'm looking for dH dt, specifically when the water's 5 feet deep, which means when the height is 5. So here we go. If we want to find something involving dV dt, then we probably need the volume. So the volume for a cone is 1/3 pi r squared h. You should know that. Okay, but here's the issue, guys. If I'm about to take the derivative of both sides, the left side's fine. The derivative would be dV dt. But if I go to take the derivative here, because I have two variables, r and h, I'm going to have to use product rule. And that's going to introduce a dr dt, which I don't want or have. So with a cone, there's a very cool thing that you can do. In this cone, do you guys see this little right triangle here made up of the height and the radius? Well, no matter what height you have, you keep getting triangles that are similar to that original, which means that the radius to the height is the same no matter how high that water is. So, for a cone, you're always going to do the ratio of the radius to the height, which in this case is 8/16 or 1/2. And I'm going to cross multiply. So I get 2r equals h, or r equals h over 2. And you're going to see in a moment why this is so nice. In this problem, instead of an r, that means then that I can replace the r with an h over 2. And now, guys, how many variables are on the right? 1, just h. You end up with h cubed over 4 times pi over 3, or pi over 12. H cubed. That makes it a heck of a lot easier to take the derivative of. So here I go. Take the derivative. dV dt. I get, bring the 3 out front. That makes it pi over 4. H squared. Don't forget your dH dt. Plug in what you know. The rate of change of volume is 2. I want it when the height is 5. And this is going to be 25. So I get 25 pi over 4. I'm going to multiply by the reciprocal of 25 pi over 4 and get 8 over 25 pi. And because this is, I'm doing the rate of change of the height, that's just a length, so that should just be feet. per second. I'm going to continue some examples in a Unit 3 video on Part B.